Welcome again to electrostatic fields. This time we are with potential gradient and energy stored. So we are still with the electric potential, and this time we'll discuss what's called the gradient. And in addition, we'll discuss the energy stored. Starting from V equal to minus integration of E dot dl, and if we apply the derivative d by dl in both sides, you will get that dv by dl equal to minus E because integration will be cancelled by the differential. Or you can say E equal to minus dv by dl, and this is actually nothing but the gradient. So E is gradient of V, and don't forget the negative sign. And the gradient, this is what we have learned in vector calculus, and based on the Cartesian or cylindrical or spherical coordinate system, you can use this equation. Now we move to the second topic today, which is energy density in a charge distribution. We will start with a system of charges Q1, Q2, Q3, and this is the final system. But let's start that we don't have any charge, and as you want to bring a charge q1 from infinity to here, since nothing is here, so bringing such a charge q1 will not spend any effort. I mean, there is no spent energy or work, so w is equal to 0 in this case. Now we have w 0. If we want to bring another charge, say q2, to this system, due to the existence of q1, there is a voltage v21 here. Then we will have W2 equal to 0, which is original here, plus something. With this something is simply the new charge multiplied by the voltage difference V21. Imagine then we want to bring another charge Q3 to the system here. You will have voltage 31 as well as another voltage V32. Then your W3, or the final W of the three charges, equal to W2, which is nothing but Q2 V21, plus the new W due to Q3, which is Q3 multiplied by V31, plus again Q3 multiplied by V32. So this is the total work done in order to bring these three charges in this specific space. This is what I have just discussed, and let's denote this equation as equation 1. If we have a charge Qi and we have voltage Vji, this can be written as the same charge Qi. Then we need to look to the other charge which caused the voltage, which is Qj, and we need to divide by 4 by epsilon naught Rji. Rji is nothing but Rij. You can replace these two charges, so you can rewrite as Qj Qi over 4 by epsilon Rij, which is nothing but Qj Vij. And if we use this one, we can rewrite W here in this form. Q2 will become Q1, V21 will be replaced by V12, Q3 V31 will be replaced by Q1 V13, and so on. And if we sum these two equations, we will find that 2W is equal to Q multiplied by something, and so on. And in summary, you can rewrite these three terms as V1, V2, V3. And if you do so, you can find that 2W equal to Q1, V1, Q2, V2, and Q3, V3. And just rewrite as W equal to half summation from I equal to 1 to 3 Qi Vi. If we generalize what we have found in the previous slide in for any charge, you can rewrite as here, just we replace 3 by n charges. And if we assume that we have a distributed charge instead of just a charge concentrated at a point, then you can calculate W as rho V multiplied by VD and integrate over the volume. And don't forget, of course, half. Let's do some analysis from what we have learned so far. We have learned first Maxwell equation, rho V equal to divergence of D. Shooting with this one, this our equation will be written as here. Recall from vector calculus that if you differentiate two functions multiplied by each other, the alpha, for example, for f and g, you can say this is just f multiplied by the derivative of g plus g multiplied by the derivative of f. And since we have nabla here, nabla is nothing but the derivative, so you can do the same for the v and d. When you do so, you will get v divergent of d plus d multiplied by the gradient of v. We already have one of these quantities here. This one is just similar to this one. So uh, doing so, we can rewrite our quantity as v multiplied by divergent d equal to nabla vd minus d gradient of v. If we do so, we reach this equation. Let's have another recall. Learn the potential gradient E equal to minus gradient of v. Substituting with this one in the equation here, you get that W equal to half triple integral nabla Vd the volume plus D multiplied by E the volume. So this is what we got in the previous slide, and let's use the divergence theorem. If we have a double integral f dot n ds, we said that this is equal to the integration of over the volume of the divergence. This time we have f equal to Vd here, and we will do the opposite. We already have the nabla vd, so we replace by the just vd and take the double integral. Doing so, this will be our result. Call that always electric field or electric flux density will be proportional to 1 over r squared, and v is also proportional to 1 over r. So this means the total term here is proportional to 1 over r squared. And if we assume our surface here, this surface S, which we are integrating over, is very big, this means that the over integral is almost tend to 0. So we can claim at the end that our term here, this one is just nothing but 0. So we can rewrite our equation here, this equation, after substituting with d equal to epsilon e, such as half triple integral epsilon e dot e in the volume. So finally, can rewrite as w equal to epsilon over 2 triple integral e squared the volume, because e dot e is nothing but e magnitude e squared. Thank you.